All right, 121 students, let me work out another orbital mechanics one. This would be number 5. And this one's got a lot of work behind the scenes, and so I'll work it out. But on a quiz, you should probably not be working out all these equations. You hopefully will just go right to your lecture notes where these were already worked out, and you can just have the equation and you can punch it in, because there's a lot going on here. Let's read this problem. It says, in the image below, the radius of the red one right here, okay, is 3.7 times bigger than the green one. So this green one has radius 1 and radius 2. So we've got the circular orbit of number 1, and it looks like a circular orbit of number 3. But what we're trying to do here, it says the energy boost, delta E, that is from the green to the yellow. So if, for the sake of discussion, let's say this is an orbit on the Earth, okay? And so here's the Earth, and we have a payload or a rocket that we want to send to Mars, which is further out and has about a circular orbit also. So we're going in a circular orbit, and the way we're going to go from Earth to Mars is we're going to follow this elliptical orbit, this orbit number 2, this yellow path. And so we're going to go from Earth, give it enough fuel, give it a boost here, and so there's an energy boost called delta E1 from the green to the yellow. That's going to put it in this orbit. And if the timing's right, Mars is going to come around, and the rocket ship is going to come around, and they're going to get real close to each other. Now, the yellow orbit would come back down this way and leave Mars, unless we give it a little more boost of energy. And so there would be a boost here, which your author called number 3, okay? And you see that right here. The boost energy, delta E3 from the green to the red, is a certain percentage of the total boost energy. So the total boost means you give it a little bit of energy to go from the green to the yellow. Then you got to give it a little bit more. There's our delta E3 to go from the yellow to the red orbit. So this right here is the total energy we need to give this rocket to go from the Earth's orbit into Mars' orbit, okay? And we're going to do it in 2 different times. We're going to do the first boost of energy during liftoff. That's usually what you see, on the news and whatnot, and maybe even had a chance to actually see a rocket launch, and you'll see this big rocket, and you'll see this fuel burning, and so you're giving it a lot of energy as we go into another orbit. But then later on in its path, it has another burning of the fuel to give it another boost of energy. Okay, now that again being said, let's go ahead and see what these numbers come out to be. And it's kind of surprising, I think, to realize that it really only depends upon the ratio of the radii. That's all the information we're given. And we can actually then figure out the percentage of energy we need for the first part of the burn compared to the last part. And we could even figure out what the energy is. So there's a lot of talk here. Let me begin by working out an equation that will, I guess, take us back to chapters 7 and 8. That if you're looking at the energy of a satellite, it's made up of 2 pieces, a kinetic energy and a potential energy. Now, the kinetic energy has to do with its speed. And I'm just going to repeat the same thing I just did on solution number 3, that if I set the gravitational force equal to the centripetal force and cancel off some common items, And so capital M is the mass of the planet we're orbiting, and M is the satellite or the rocket that we're sending. We get a nice mathematical relationship for the velocity. Now, I hope that wasn't too fast. If you want, go back to the video for number 3, and that's what I worked out right here for number 3 at the beginning, how much speed that each of a satellite has to have. All right. Now, again, the reason that's useful is when it comes to calculating the total energy, then, in place of V squared, I could put G M over R. And so I've got my 1/2, oh, I forgot my little m. And so 1/2 times the mass of the rocket times G, the gravitational constant, times the mass of the planet divided by R. Now, I deliberately didn't put anything for the potential energy here for just a second, because up until this chapter, you always said something like the gravitational potential energy is mgh or mgy. And, of course, you got that by saying, well, energy is force times distance, and on the surface of the Earth, you pull things up in a y direction, and the force of gravity is mg. So if you integrate mgy, you get, mg dy, you get mgy, or just mgh. Now, that would only be true if the force of gravity was always mg, but what we're learning in this chapter is that the force of gravity is this universal law of gravity, which is approximately a constant near the surface of the Earth. So this mg that we've been using in the past, we're going to have to throw away as we get into this chapter, because it's not valid in this chapter. This was only true if we didn't change the radius much. And so if you talk about an airplane, an airplane just doesn't go very high compared to the radius of the Earth. And so really the force of gravity doesn't change much. But a rocket ship can go really, really high, and the force of gravity can really change. And in this case, the force of gravity would dramatically change as we left here and went to here. And so as we go from the Earth's orbit to the Mars orbit, changed by a lot. So really, to answer this question of what equation do I use for the potential energy for problems that go, what I like to say, go out of the atmosphere, I've got to integrate the Gm times m r squared, and we would be going away from the Earth. Let me just call that the radial direction. But I hope you're seeing I'm doing the same math here as we did in chapter 7 and 8, where we just integrated the force of gravity. It was just a much easier integral because we just had mg. And so now when I do this integral, I got an integral of dr over r squared, which then becomes, let's see, I can think of that as r to the negative 2. So this would be r to the negative 1 divided by negative 1, which would simplify. I'll put the negative up top, and I will then change the negative exponent to a positive exponent. So that's what goes in here. So negative g big M little m over r. And these are like terms, so they can be combined. So this has a g, a big M, a little m over an r. They both do. But here I have a positive 1/2, and here I have a negative 1, which means we get a negative 1/2 when it's all said and done. All right, so hopefully you started this quiz already knowing this equation. So I hope I didn't waste 9 minutes of your time working through this very important equation to solve this problem, because it has to do with energy. But this is the energy of an orbit. Now, I'll also say that everything I've done really was dependent upon them being in a circular orbit. And we have two circular orbits. The green one and the red one are circular orbits. But the yellow one is actually elliptical. All right. So let's talk about ellipses for a moment. And some ellipses, we draw, oh, that was a terrible ellipse, horizontally. Others we draw vertically. But the distance of the long side is called the major axis. And half of it is called the semi-major axis. And we usually label that with an A. Whereas the other one, the short axis, is called the minor axis, and half of its distance is called the semi-minor axis. But here's what's kind of neat, is as this moves around, it is sometimes further than A, and sometimes closer than A, but on average, it is an A distance away. And what I'm trying to say here is a elliptical orbit can be thought of as a circular orbit, at least in terms of energy, with a radius of A. So in other words, if I just put A into this equation, I would have the equation for the energy of an elliptical orbit. Now, the math to prove that is a little bit lengthy, and so let me not get bogged down into that rabbit hole, but let me just say then, I can apply this equation then to all three orbits. I can apply it to orbit number 1 and orbit number 2. I'm just going to have to use the semi-major axis for number 2, and then I can apply it to number 3 just as well. Okay? So I would then say this, that what your author calls delta E1, and I'll also match it with delta E3. He's saying this is the energy difference, how much energy you have to boost it by, how much energy you have to give it to go from number 1 into number 2. And so I will say this is the energy in number 2 minus the energy in number 1. And so using this formula here, I might say it would be minus G big M little m over 2A. That is how much energy I would have when I'm in the yellow orbit. And then minus G M over 2 R1 is how much energy it has when it's in orbit number 1. And I'll simplify that a little bit. And let me just factor out a G and a big M and a little m and even a 2. And then these two negatives will make a positive. Let me write that first. That would be 1 over R1, and then this would be minus 1 over A. So that would be my mathematical equation for the change in energy, or the boost in energy, number 1. Now, the boost in energy for number 3 is kind of the same idea. The energy I have once I get into orbit number 3, so I'll put radius number 3. And then minus the energy I have when I'm in number 2, which again, that's that elliptical orbit, so I'll treat it as an A. And then again, I'll simplify it, noting that they each have a G, a capital M, a lower m, and a 2. And then these two negatives would make a positive, so I'd have a 1 over an A, and then this would make a minus 1 over R3. Okay? So let me not do too much with that yet, but let's see if we can kind of head in the direction that they want me to get. They say, because here's the answer we're trying to get to. Oh, and it looks like I don't have the correct answer here. So I hope I do this right. But delta E is a percentage of the total. So what they're really asking is delta E1 over the total energy, which is delta E1 plus delta E3. And as a percentage, then times 100. So how much energy do I give it for the first boost compared to the whole boost? Because remember, a fraction is a part over the whole. So here's the whole energy I got to give. This is the fraction for the first one. And that's what they want to know. And to make it a percentage, then I multiply by 100. But here's what I'm going to just kind of simplify. I'm going to take this delta E and move it downstairs. So this becomes a delta E over a delta E1, and then a delta E3 over a delta E1. Oh, times 100. Because then this just becomes 1 times, or 1 divided by 1 plus, and then this is energy of number 3 over energy of number 1. And then of course times 100. So this is going to be the key step, because this ratio I can get right here. I can just divide these two. Okay. And like I said, orbit mechanics loves to do a bunch of ratios. And you can see why, because these things that show up for each one cancel off. The only thing that varies is the radii, and that's why we're going to have the ability to answer this question just on the information of the radii. Okay? So I'll continue here. So let me go delta E3 over delta E1. I'm going to use that, or these up here, to get that number so I can get a percentage here. So this is going to have a bunch of math here, because the top one's going to have this G M M over 2, 1 over A minus 1 over R3. And this one here is going to have this G M M over 2, 1 over R1 minus 1 over A. And those extra factors drop off. That's good. And now, maybe I'll just make a compound fraction first. I'll get a common denominator of A times R3. That means over here I got to multiply by R3, and over here I got to multiply by A. And then likewise in the denominator, if I get a common denominator of A over R1, then I'm going to get an A minus R1. And so now if I flip and multiply, so R3 minus A over AR3, and then flip it, AR1 over A minus R1. This A cancels off, and it looks like I'll have an R3 minus A on the top here with a R1. And then on the bottom I have an R3, so I'm going to group my R3 here. And then this would be an A minus an R1. All right. Now, guess I still have some significant work to do, because this ratio I would like to be in terms of the ratio of the R1 to the R2. And that second factor is, but this first factor has got these A's in it. And this may not look like it, but these are actually, this ratio is actually 1. It's got an A in it, and it's hard to see it right now, but let's keep working on this for a moment. Maybe I'll come back to the picture. But if you look at this ellipse, and you look at the yellow one, this whole distance across here is the 2A I was talking about. This is the major axis of it. But if you also look at it, that distance is also the radii of the green one plus the radii of the red one, right? This is from the planet on to the red one, that's R3. And from the planet on down, that's R1. So this is the same as R1 plus R3. Okay. And like I said, it may not look like it at first, but if I move this R1 to the other side, so minus R1, and I leave my R3 here, and then I take this 2A, and I take one of the A's and I bring it over, minus A, and I leave the other A over here, you can now see that A minus R1, this right here, is the same as R3 minus A. So that is, the same number on top as the bottom. So that's just a 1. So that's a bit involved with the geometry to see that. But it actually then comes out surprisingly simple that this ratio of the energies is just the same as the ratio of the radii. All right, so I'm going to use that back here so I can finally answer this question. Okay, so to answer this question, I will put this as 1 over 1 plus, and so again, 3 divided by 1. 3 divided by 1 is R1 divided by R3, and then times 100. And coming back to this problem now, they say in the image below, the red orbit, so that's the R2, is 3.7 times bigger than R1. Oh, I'm sorry, this is R3. R3 is 3.7 times bigger than R1. Or in other words, R1 over R3 is 1 over 3.7. Which, if I just put that into my calculator as 1 divided by 3.7, I get 0.270, 0.270. And I'm going to put that then right into there and get an answer. So in the bottom, I have 1 plus this last answer. So that's the bottom of it. And then I'm going to take the reciprocal of that. And then that's the fraction, and so times then 100 makes it the percentage. So 78.7% of the energy occurs on the first boost. And so there is the first boost. Yay! Hopefully that was helpful and not too long-winded. All right, take care.